Hello everyone. So we will do the hands-on for module 4 now. You'll find the hands-on description of the module on the NSA course folder. Let me go to that folder. Inside the labs, so you'll go to the NSA course, module 4, online stream analytics, labs, and lab 1. It's the lab 1, so you have to open the lab 1 document. So this document actually explains what you have to do and all the necessary requirements. So basically in this labs on, in this hands-on, we will predict anomaly from the IoT stream data. So we'll try to find if any data stream coming from any IoT device has any anomaly or outliers or not. So basically this is done with the clustering algorithms that Professor described or explained earlier. So the basic idea is we'll collect the data from the IoT device or any IoT device. We'll build some clusters, and once we go to the testing phase, we collect the data from the IoT device, and if it falls to any of the clusters that we built previously, it will be predicted as a benign data point, and if it does not fall into any of the clusters, it will be predicted as an anomaly. So this is the basic idea. So for this exercise, we'll be using the FullBot air quality monitor sensor. This is, you can see it right here. So it can, yesterday I've told you about this. It can measure carbon dioxide level, temperature, humidity. So we'll be using these 3 values. I mean, this sensor will give us these 3 values. And we'll be using these 3 values to detect anomaly. That is, if the sensor is, if the data stream coming from the sensor has an anomaly or not. So we'll be using this device, and on those 3 values, carbon dioxide level, temperature, and the humidity. So once we get the data, we'll build the clusters, and for that, we'll be using the incremental clustering technique. And in real world setting, usually we'll have to deal with multiple IoT devices. Even if we deal with one device, it will emit lots of data in a streaming nature. So we have to deal with the streaming nature of the data. So for that, we'll be using Spark streaming and also the Kafka. So you will find the details of the problem statement here. So one of the limitations, as Professor told you about earlier, that for FullBot device, we can only request only 200 data instances per day. So it's not that much data. So what we do in this case is that we collect the data beforehand and store it in a database. Actually, for our case, we are using MongoDB. And from this database, we fetch the data and build the clusters that we talked about, the incremental clusterings offline. So we cannot do it online because of the limitation of the device. But if we use any other IoT device, that might not be the case. Maybe we can do it in real time, build the models in real time, not offline. But in this case, we build the models offline, storing the data in the MongoDB for a couple of days, and then we fetch the data and build the model offline. And for the testing case, we will fetch the data in real time from the device. We fetch the data in real time from the device, and then using the pre-built models, we will try to determine if the data coming from this device is anomaly or benign. So this is basically the gist of the solution. I mean, how we are trying to solve it. So let's, if you have not downloaded the code yet, please download the folder Lab 1 Solutions. We'll go through the code first, how the code is working, and after that, we'll run the codes. So for this Labs on, we'll be using, as I said, we'll be using Spark Streaming and Kafka. But yesterday you also used Spark Streaming and Kafka. But in this exercise, we'll do it in a different way a little bit. So yesterday you used the Kafka and Spark Streaming on the same machine. So the producer and consumer will be on the same machine, was in the same machine. So, but in this case, as we have the limitation of only 200 requests per day, we'll be using producer in a different machine and consumer in a different machine. So your machines will be all consumers, and producer will be me. So I will get the data from this and send it to all of you guys. So that's why before running the code, we need to understand how it's working. So please download the codes from the Lab 1 solution. So first, let's open Python. So you have to open the dashboard folder from the Python, this one. So this is the Python program. So for this project, we are using both Python and Java. So Python is the producer here. This is the dashboard program. Then you have to open IntelliJ IDEA. You'll find it here in the menu. Here, click here, and then this one. So for the from the PyCharm ID, open this file Kafka prod version 2. Can you read here? That is shown here. And from IntelliJ IDEA, you have to open this Anomaly Detection Spark folder from the Lab 1 solutions. So this is the Java code, and we will run this on IntelliJ IDEA, the Java IDE for Java.
What was that file on the
It's called Anomaly Detection Spark folder.
Yeah,
Oh, okay.
It's the folder file.
It's a folder. You have to open that project
So
folder.
just choose the folder.
Sorry?
Just choose the folder.
Oh yeah, choose the folder, right. Just choose the folder. From open, choose the folder.
Yeah, start with Java.
Yeah, so this Anomaly Detection Spark, this project is the consumer here, so it is written in Java. And the dashboard, the project called dashboard, it is the producer, and it is written in Python. All right. So let's briefly go through the code first. I'll explain the producer first, how we are collecting the data and storing in MongoDB, and then sending it to the consumer to classify, and then I'll explain how the consumer is working. I mean how the anomaly detection part is working. So in the Python code, if you go to the Kafka prod v2 file, .py file, so everyone was able to open these two projects. Anybody has difficulty, please let me know. Okay. So in the main method, we can see that it's creating some threads, and after creating thread, we are going to this function. So what it does is, so first we have some training period and we have a testing period, right? So in the training period, we collect the data from the devices and store it in MongoDB. And after that, from the test period, we collect the data from the MongoDB and send it to the Spark, where we build the models offline using the historical data. And then we collect the data from the device in real time, and using that models, we predict the anomaly or anomaly. So this is the training period. If the training period is on, then we collect the data from the DB, send the data to the consumer from the DB. So we already have stored some data in the MongoDB. The machine is in our lab. So if you want to know how we collected the data and how we stored the data in the MongoDB, you can open these two files. Actually, you can go through these two files, which is Kafka prod and Kafka consumer. Kafka prod will collect the data from this device in 300 seconds. Like every 300 seconds or every 5 minutes, we'll request the device to send us some new data. And once we get the data, we use the Kafka to send it through the consumer. So in the consumer part, we are getting the data and store it in MongoDB. So how we store the data in the MongoDB, you can learn this process from these two files, but I'm not going to go through these files because we already stored the data in the MongoDB. So after we store the data in the MongoDB, we get the data. So this function actually gets the data from the DB. You can find the MongoDB credentials here. So this is the IP address of our machine in our lab. This is the port. The database call is fubot2. So from this database, we get the data. We kind of clear the data because, as I said, we'll be using the humidity, temperature, and the carbon dioxide levels. So we only get these three values. And we pre-process the data using the scikit-learn's default standard scalar method. After we pre-process the data, we So after we pre-process the data, we send the data to the Kafka. So here the topic name is IoT2. I think you are already familiar with the Kafka by now. So the topic name is IoT2, and we'll be waiting for some seconds. For this, I think it's 1, or maybe if you want to see the output in an interval manner, then you can increase the wait time seconds to 3 maybe or 5. It's up to you. So in this part, we only just get the data from the database and send it to Kafka, to the consumer. So now, if we go to the consumer program, which is the Java one, and please don't run the program now because, as I said, the producer will be here and the consumer will be all you guys. So we'll run the program later. Okay. So now in the consumer side, it's written in Java. So you can see, so if you go to the main method, we first initialize the Spark configuration. We start the Spark streaming context. So in this line, we specify the Spark configuration, what kind of configuration it will have. Whether we have given an app name, you can change the app name according to your likings. And you have to set the master. So the master is the master node of the Spark cluster. So as we are running Spark locally, so we have used local. And if you have a remote master, then you have to use the IP of the master and the port. So local and the star means actually we are using all the available cores that we have in our machine to run the program parallelly. So that's why it starts. If we use 2, then it will only use 2 cores. If we use 2, it will only use 2 cores. So, okay. Then we create a Spark streaming context using the configuration. Here, duration seconds means every 2 seconds we will capture the batch that's coming through the Kafka to the Spark streaming. You can also change this value to 1. If you set it to 1, then every 1 second you will capture the data. If you set it to 5, every 5 seconds you will capture the data. Okay. So next, we are creating the Kafka streams using the topic. So when you run this program, you have to also say the topic name, because this is how Kafka works. The topic name needs to match. So here the topic is IoT2, right? Yeah, so IoT2. So when you run the code, you also have to define the topic name. You need to make sure the topic name matches. So let's go to how we are building the clustering part. So we have, so we have the data points. Remember, from the producer, we are passing only 3 values. There is humidity, temperature, and the carbon dioxide levels. And here we are getting those 3 values. And yeah, these are the points. So this is an array of strings. So we only have 3 values in this array. And here, get nearest cluster function, you can see, we are trying to get all the nearest cluster or any nearest cluster that this point belongs to. So here in the program, we are maintaining a list of clusters that we have built. So if the data point is the first point, then we don't have any clusters. We don't have any clusters right now. So this will be the first point. So if this is the first point, if it does not belong to any cluster, then it will create a cluster. You can see this logic in this function. You can find this in incmin dot get nearest cluster function. So this is the file, and dot get nearest cluster. So if you see this function, you'll understand. So here we are trying to find if the newly incoming data point if it falls into any cluster or not. If it doesn't, then we will create a singular cluster with only that data point. If it falls into that data point, into any cluster, then it will return a cluster, the cluster that it falls. And Professor already mentioned that how to determine if any data point falls into a cluster or not. We will be using Euclidean distance to measure the centroids. So we have a cluster with a centroid, and we have a newly incoming data point. We'll just measure the distance between the centroid of the cluster and the data point. So suppose we have a cluster. Suppose we have a cluster. This is the centroid, which is suppose C1, C2, and C3. And we've got a new data point. So this is the data point. We suppose it's X, Y, and Z. So we'll measure the distance between these two. And if it's within a threshold, then we will say that it falls into this cluster. And if it doesn't, if it doesn't fall into any other clusters, then we'll create a new cluster with just this point. So in this map to pair function, we only do this process. So as Professor said, we'll be using MapReduce. So this is the map function, and the map function will return a key value pair. So in this case, suppose this suppose this newly incoming data point falls into this cluster. So the map will emit the centroid of the cluster that the new data point falls into. So map will emit a key value pair. The key will be the center of the cluster, and the value will be the newly incoming data point. And along with that, the number of points. So in that case, we are only dealing with one data point at a time. So it will be 1, the count of the data point. So this is the key, and this is the value. Suppose another data point comes. So let's say it's ABC, and it also falls into this same cluster. So the key value, so the map will emit a key value pair, and the key will be this one again, the cluster centroid. And value will be ABC. You can see it from here. This is the tuple. So this is the key, the center, and the point with count. The point is the XYZ and the count is 1. It will be always 1. So, and if it does not fall into any cluster, then the center and the point will be the same thing. So XYZ, here it will be also XYZ. So the map function will do this. It will always create a key value pair. So if we go to the reduce, the else is for the training, is for the testing phase. So we'll see that a little bit later. So we are only going through the training phase now. So in the reduce by key, if you check the training phase, this is this F. We are summing all the data points that belongs to the same cluster, newly incoming data points that belongs to the same cluster. For this case, we have 2 data points that belongs to the same cluster. So this is the key. So for each key, the values will reduce by key function will operate on those key value pairs that has the same key, that have the same key. So in the key value function, we will get this value and this value. And in this function, we are just summing the data points. That's it, according to their coordinates. So we'll just sum these data points. That is, after the reduce by key, it will emit a value that is just x plus a plus b plus c. And also these are 2 points, that's why we will be adding these 2 values as well. 1 plus 1, which will be 2. So this indicates that we are just summing the 2 data points according to their coordinates, and the number of points is 2. So the reduce by key will only emit this one, this value. Now, so we have got 2 data points with these coordinates, and it falls into the same cluster. So now we have to update the cluster. So this is done in map function, the second map function that we have in the code. If you can see the training phase, in the update cluster method, so the so here the key will be this one as usual, and the value will be this one. So in the update cluster method, as professor already explained, that we will be using the weighted average. So we'll take the average with the existing data points that this cluster has. So for weighted average, suppose this cluster have 5 instances already, and we have 2 instances. So in the update cluster method, we'll take the weighted average. That is, let's see, 1 So in same manner, we will calculate C3 prime. So for the reason that we are using the weighted average is that it already has some data points, like 5 data points, and we have to recalculate the cluster centroid. So we are trying to place the centroid as much as possible to this side, because it has the maximum number of points, more points in this side rather than the normal one. If the newly incoming data points are larger than this number, then the centroid will shift to that side more. So this is how we update the cluster and the cluster centroids. And finally, we emit some cluster information. So each cluster has some IDs. We are storing the cluster, remember, so we give each cluster IDs, and we have the member counts and the cluster centroid coordinates. So we emit these numbers to visualize in the, what is it called, Kibana. So we store this information in the Elasticsearch, and from Elasticsearch we do the visualization in Kibana. So this is basically the gist of the thing. So this is our algorithm. So we get the data points. We check if it falls to any cluster or not. If it doesn't, it emits a new cluster. If it does, then we update the cluster. So it goes on until all the training data points is over. So after that, we have the build clusters, all the clusters that we have. And after we have the clusters, we resume the testing phase, which is where we try to predict if the data has anomaly or not. So up to this point, anybody has any questions? All right. So if we go to the Python file again, all right. So now, if when all the data is sent to the consumer for training, we will start the testing phase. So in real time, we'll get the data. So this is happening in this function, send data from device. So this is the headers where we have to mention the API key token. So for each device, there is a key token, I guess. So when you have to get the API key token, you have to you sign up for the full bot, and they will give you token. So, and for each device, they have an ID. So for this device, the ID is this one. Then we use the API call to get the data. The call is this, the HTTPS API call. So you can see that we are actually fetching more than 3 values. We are also fetching air pollution percentage, but we'll be using only these three. So the data comes in a JSON format. So we parse the data, then we normalize the data. So in this case, one request will give you one data instance. Then we sleep for some time, because for this fullbot device, it will give you new data in every 5 minutes. So if you request 2 instances within 5 minutes, then they will just give you the average of the 5 minutes. So you might get the same data again. So it's better to call the fullbot this device for the new data after 5 minutes. So we pre-process. We normalize the data, and then we send it to. So when we send it to Kafka again with the same topic name. So the same consumer will get the this real-time data. Yeah. Sure.
Just a point, my sleep time says 30 seconds. Should it be 300 seconds?
Yeah, it was 30 seconds. You can just change it. I changed it here, 300. It's up to you. You can use any time, but if you use it, if you call twice in 300 seconds, then it will give you same data. But you will get data. Okay. So the testing phase now begins. So we already have set up this Spark streaming things, configuration. So if so for the first map, you will see if the training phase is over. So you don't go to this point. It was else. So here we are actually predefining the training points. How many number of training points we will be using. So here we'll just use 100 points, but if you have data, more data in database, you can also do that. So the testing phase. So now, when the new data comes from this device in real time, so this is the real time data. So we'll just check if this data instance falls into any of the clusters that we have built before. So this is done in this function. You can go to this function if it falls.
Could you zoom in?
Sorry?
Zoom in on the test.
Oh, zoom in. Okay, sure. Okay. Okay. Is it better now? Okay, thank you. So if you go to the is fit in cluster function, so here it will check if the newly incoming data point is it falls into any of the previous clusters or not. It will depending on that, it will just return true or false. So you'll just know if it falls, if it's a benign or an anomaly. Okay. So this is a map function. So this function always returns true or false. So if it is true, that means that it falls into any cluster, and that means it's a benign. And if it does not fall into cluster, it will output only outlier. So it will emit a key value pair, and if it's a benign, then it will just output benign with the count of the data points. As I said before, that we are only handling one data point at a time, so it will be just one, the count. This is the key, this is the value, and if it's an outlier, then it will just emit outlier, one, key, and the value. And if you go to the reduce function, so the map will emit this key value pair. So if you go to the reduce function, so this portion is the testing phase. It will just count the number of benign or outlier data points that we encounter. So if for each key, so here the key is the benign. So if you have like 3 benign points, the reduce key, 3 benign data points, the reduce by key function will get those 3 points and it will just add them up. So and emit a key value pair that is just benign, which is 3, just add the count. So that way we'll know how many benign points and how many outliers we got. And the second map function, we are just structuring the data so that we can visualize in Kibana. Nothing else. So we are just creating a map object with the prediction and the count of the prediction. In this case, prediction is the benign or outlier, or count is the number of benign or number of outlier points we got here. So finally, once we have all this, we are using the Elasticsearch to save the results. So it also saves the benign outlier information as well as the cluster information into the Elasticsearch. So we are creating an index here. This is the index and this is the document type. So here we are just saying that all the document is the clusters. And this is the index. Under this index, all the values will be stored. And using this index, we have to visualize in the Kibana. So this is basically how we are trying to detect the anomaly. So anybody has any questions so far? Okay, let's just run the program now. First, please open the README file. It's the version 2, README v2 file. So you have to, like yesterday, you have to start all these processes. Let's start these processes first. Zookeeper, Apache Kafka, Spark, Elasticsearch, and Kibana in the terminal. So I think you already opened the project, Anomaly Detection Spark project in IntelliJ IDEA. So you have to do two more things. That is, you can see this box here. Import Maven project needs to be imported. You can just enable auto import. This thing. Enable auto import. So it will just import the Maven library in your IntelliJ IDEA IDE. And after that, you have to delete one file here. So instruction is written here. So you have to go to that folder, Anomaly Detection Spark. If you have any difficulties, let me know, please. So you have to go to, next you have to go to Anomaly Detection Spark folder, then source, then main, then delete this resources file. Actually, it was supposed to be a folder, but when you download it in Linux from the Google Drive, it becomes a file and it gives an error if you run the code. So it's better if we just move the trash. Yeah, delete the file, that file, resources file. All right. So if you open the Anomaly Detection Spark project, after doing all those things, open this project and go to edit configurations. So this is the IP of the producer that you're trying to, I mean not the producer, I mean the Zookeeper broker, I mean Kafka broker IP. So basically you are connecting to this Kafka side and fetching the data which has the topic name IT2. Now, so before running the program, you have to change this name. This is the consumer name. So each consumer has a name. So for this, you have to actually use a unique name here. So as I've said here, that please try to give a unique name in the consumer one. If two machines have the same consumer name, then those two machines might not get all the data. So data might be divided into partitions. So suppose I have 100 data points, 50, one machine will get 50, one machine maybe will get 50. So try to give us unique name here and then OK.
Change to something.
Something else here. Okay, I'm going to switch it to my laptop here. Okay. As the machine is in our lab, we will connect to the machine remotely. So if everybody is done with this part, I can run the producer, then you'll be able to get the data. So please run this code using this right click and then run Java Kafka K-means and see if there is any error or not.